Hi, welcome back to Math 533, Topics in Euclidean Geometry. This is the beginning of our third module, and this module, the last module of the semester, is about the most important topic in Euclidean geometry, which is that of similarity. So a key feature that separates Euclidean geometry from, let's say, hyperbolic geometry is the fact that you can scale things in a way that's interesting and meaningful. And we're going to look at that in some depth, and we're going to study it from multiple different angles. So this week, we're going to start talking about similarity transformations, and we will use that to build up the idea of similarity of triangles, especially, but of shapes in general, but most importantly, of triangles. Then in subsequent weeks, we will talk about things like area, and eventually we will get to the most famous theorem in geometry, the Pythagorean theorem. But first, let's talk about similarity transformations. Now, the first thing we're going to want to do is we want to define this. And this is a deeply important topic in Euclidean geometry. And actually, in this week, we're going to be looking at a theorem that is traditionally attributed to Thales of Miletus, who was a Greek mathematician and philosopher active around 600 BCE. I'll mention that his writings have not survived for us, and so we don't actually know if he did this theorem or not. It's later Greek writers who attributed the work to him. Okay, so let's kick this off with a definition. We are going to first define a similarity transformation. So in this, we're not at all following in the footsteps of Thales. This idea of transformation, I believe, is a later one. But our idea is that a similarity transformation is a transformation of the plane that scales all distances by a constant factor. Now, we're going to call it a similarity transformation in this class, but I should point out that other sources talk about it as just a similarity or as a similitude. Okay, so our definition is that T is a similarity transformation if there exists a positive constant, so that for every pair of points x and y in the plane, if we write T of x to be x prime and T of y to be y prime, then we want the distance from x prime to y prime, which we denote by x prime, y prime, we want that to be that constant c times the distance from x to y. And we will call this number c the similarity ratio of the transformation T. Now I want you to notice here, if c equals 1, this is the same thing as an isometry, right? So an isometry is a special case of a similarity transformation. The big question is, why do we have c greater than 0? That's something we put in our definition, of course, so it's forced on us. But the question I want you to think about is, why is that the only sensible thing to put in here at this point? Okay, now we can define what it means for two shapes to be similar. We will say that two shapes are similar if there exists a similarity transformation that sends the first shape to the second shape. And then we're going to denote this relationship with a tilde. So for instance, if we want to denote that triangles ABC and DEF are similar, we will write triangle ABC with that tilde symbol, triangle DEF. And this relationship, I'll have you think about it for a little bit, but that relationship is an equivalence relation. Okay, so let's consider a couple of examples here. One example is if I have a pair of congruent triangles, those triangles are automatically similar, right? That's by what I said before. If I have congruent triangles, there's an isometry that maps one to the other. And an isometry is a special case of a similarity transformation. Okay, here are some less obvious examples. If you give me any two equilateral triangles, they're automatically similar to each other. Any two circles are similar to each other. And any two squares are similar to each other. And the reason for that is you can imagine scaling. If you have your two favorite equilateral triangles, the only difference between them is the size. So you can scale the small one up to get the big one, or you can take the big one and scale it down to get the small one. So let's talk about a very important special similarity transformation. And this is something we're going to call a dilation, or in some other places in the literature call it a homothetic transformation. But we're going to call it a dilation. For this, I want to fix a constant c that's positive, and I want to fix a point O. And what I'm going to think of doing is saying that the dilation t of ratio c just rescales everything from O, either outwards if c is greater than 1 or inwards if c is less than 1. So we define it as follows. We say t of O is O, and for any x, right, so for any point x that is different from the point O, we define x prime to be the unique point on the ray OX, so that OX prime is c times OX. Right? So the distance from O to x prime is c times the distance from O to x. And we're going to notice that the inverse of the dilation centered at O of ratio c is the dilation centered at O of ratio 1 over c. Okay, so we have a structure theorem for similarity transformations. If you fix your favorite point O in the plane, so it's an arbitrary point in the plane, we just fix it for now, and then we're going to write d sub c for the dilation centered at O of ratio c. And now we have this important fact that any similarity transformation of the plane of ratio c is obtained as the composition of a dilation centered at O of ratio c with some isometry. So this means that basically once you understand isometries and you understand dilations, then you understand all the similarity transformations. Okay, so now we're going to state a few theorems about similarity, and we'll prove some of these later. So the first one is the so-called side-side-side similar triangles theorem. So this is only in the context of triangles. So we say if we have two triangles, ABC and DEF, these two triangles are similar if and only if there exists a positive constant c so that the sides are in the same ratio with each other. So DE is c times AB, DF is c times AC, and EF is c times BC. But this theorem is not super difficult to prove, but we will postpone the proof of this for a little bit later because we need some tools before we can talk about that fully. Then we have a much more fundamental theorem on similar triangles, the angle-angle-angle similar triangles theorem. So this tells us that two triangles ABC and DEF are similar if and only if their corresponding angles are congruent to each other. And so angle of A in A is congruent to the angle in D, the angle in B is congruent to the angle in E, and the angle in C is congruent to the angle in F. And this is such a fundamental theorem that sometimes this is used as the definition of similar triangles. And then the ratio property that we had in our previous theorem, the side-side-side similar triangles theorem, is then seen as a consequence. But we're going to say, right, so for us, the definition of similarity has to do with the similarity transformation. And this then is a theorem about what that means for triangles. Now, to prove this, we're going to need a very important and slightly technical theorem called all sorts of different names. We're going to call it the Basic Proportionality Theorem. I'm using language from Wikipedia in doing that. And it's one of the two theorems that are attributed to Thales of Miletus. Okay, so this is the statement of the Basic Proportionality Theorem. And it's also sometimes called the Intercept Theorem. And it's also sometimes called the Parallel Projection Theorem. We'll revisit that a little bit later. But let's state the theorem here. So we're given a configuration that looks like my diagram here on the right. So we have two lines intersecting in S. We have 2 points on the first line, A1 and B1, and we have it in the order S, A1, B1. And so A1 is in between S and B1. And on the second line, we have S, A2, and B2 in that order. And we consider these lines here that connect A1 and A2, and then the line that connects B1 and B2. And the theorem that we have, this is the Basic Proportionality Theorem, that those two lines are parallel if and only if the ratios of the distances here, the ratio SA1 over SB1, is equal to the ratio SA2 over SB2. And this is the fundamental theorem that's going to make both of our previous theorems on similar triangles work. Okay, that's it for this video. I'm leaving you on a cliffhanger here because, of course, we're not going to prove these in this video. We will prove the theorem of Thales in our next video, but then we will save our other two theorems that we had here on similarity. We're going to save them in part for the homework and in part for next week. See you on the next one. Thank you for watching, and happy mathing.